This is the 33rd video in a series that I'm making to support a course that I'm teaching in elementary number theory. And we've been working with integer partitions and Q series, really focusing the end of this course on a brief preview of the number theory of Ramanujan. And so in the last video, we proved something called the Jacobi triple product. And today we want to prove something called Jacobi's identity. And then we'll use that to prove a very important and famous congruence that Ramanujan proved about integer partitions. Okay, so let's look at Jacobi's identity. So that's the sum as n goes from 0 to infinity of minus 1 to the n, 2n plus 1 times q to the n plus 1 over 2 is equal to this Pockhammer symbol q infinity cubed. Okay, so let's jump into the proof of this, and you see that the proof of this, along with this thing that we did in the last video, will be used to prove that Ramanujan congruence. Okay, so like with many of these identities, we're going to start with ones that we have already proven and make some substitutions. So we'll start with the Jacobi triple product. So I'll just say that we will start with Jacobi triple product, and then we'll make a substitution. And which substitution will we make here? Well, I'm going to replace z with z squared times q. Okay, so let's see what that gives us. So that's going to turn our left-hand side into this sum as n goes from minus infinity up to infinity of q to the n squared plus n. So we get an extra multiple of q from replacing z with z squared times q, and then we have z to the 2n. Okay, so we've got something like that. And maybe motivating this substitution is the fact that here we have n times n plus 1, and obviously n squared plus n will factor as n times n plus 1. You might say, well, what about this 2 in the denominator? Well, we'll take care of that later. And then what happens to the right-hand side under this substitution? Well, this guy right here will turn into minus z squared, q squared. Then this guy right here will turn into minus 1 over z squared, q squared. And then the last thing stays itself. So we'll have q squared. Okay, nice. Now next up, we want to take this middle term and expand it out. And then look at it and see if we can tweak it in a way so that it is a little bit more helpful. So we'll get 1 plus 1 over z squared, that's the first term, times 1 plus q squared over z squared. That's my second term. 1 plus q to the 4th over z squared. That's the third term, and that's an infinite product. Now, we'd probably like this middle product to have a similar format to this first product. So in other words, maybe it should include a q squared in the first entry. And we can have it include a q squared in the first entry if we start it here. In other words, if we take off the first term of the product. So let's notice that all of this stuff that I've underlined in pink is in fact minus q squared over z squared, q squared, infinity. But how can we get rid of this 1 plus 1 over z squared? Well, we'll just divide it to the other side of the equation. So that'll leave us with 1 over 1 plus 1 over z squared times this sum as n goes from minus infinity to infinity of q to the n squared plus n, z to the 2n. And then over here on the right, we'll have minus z squared, q squared, and then minus q squared over z squared, q squared, and then q squared, infinity. Great, so we have built that. And then we'll notice that if we substitute z equals I into this right-hand side of the equation, we have 3 copies of this q squared. That's because I squared is -1, and that'll cancel this. Well, we can't exactly just set z equal to I, but we can take the limit. So let's do that. So here we'll take the limit as z approaches I of this whole right-hand side, and that's going to turn this into q squared, cubed, but that's infinity. So q squared, infinity cubed. That's because this first term and this second term transform into this third term by this limit. Now, what can we do with this left-hand side? Well, I'm gonna rewrite it involving the limit, and then we'll do the calculation starting at the beginning of the next board. So this will be the limit as z approaches I of the sum as n goes from minus infinity to infinity of q to the n squared plus n times z to the 2n plus 1. You might say, well, how did that become 2n plus 1 when it was 2n? But it did because we'll take this and multiply the numerator and the denominator by z. You might say, well, what's the motivation for that? Well, let's notice that this 2n plus 1 will now match this 2n plus 1 that is out front of everything. So we really want to get a 2n plus 1 involved in this whole situation. But what is that going to leave us in the denominator? We will have z plus 1 over z, like that. So now let's bring this last line to the top, and then we'll continue on. On the last board, we were able to show that q squared, infinity cubed was equal to this limit as z goes to I of all of this stuff. Now, before we start taking this limit, now I want to maybe replace q with q to the half or the square root of q. So I'll just put this in yellow that we're going to replace q with q to the half. So what effect will that have? Well, that's going to change these q squareds just to q's. So we have q infinity cubed. And then over here, we'll have a 2 in the denominator, which is actually quite nice because this n squared plus n over 2 is exactly this n times n plus 1 over 2. So now at least the q's are looking right. Okay, so now let's take this limit. But if you look at this, notice that it is an indeterminate form. If you plug z equals I into this denominator, you get I plus 1 over I. But it's well known that 1 over I is equal to minus I, so that gives you a 0 in the denominator. And then furthermore, there's a 0 in the numerator. That's a little bit harder to check, but maybe that's a good homework problem. And that is check this numerator equals 0 if z is approaching I. So maybe I'll leave that as a little bit of a homework exercise. But that means that we have an indeterminate form, we can apply L'Hopital's rule. So just like from calculus. So I think it's kind of nice when tricks from maybe an early math class show up in later math classes like this. So we'll apply L'Hopital's rule. That'll leave us with this limit as z goes to I of my sum as n goes from minus infinity to infinity of 2n plus 1 times z to the 2n, and then we have q to the n times n plus 1 over 2, and then in the denominator we have 1 minus 1 over z squared. Now let's see what happens as z approaches I. So this will leave us with I squared to the n, really I to the 2n, but using exponent rules, that's what that simplifies to. But that's minus 1 to the n. So that's good. And then this will be 1 minus 1 over minus 1. In other words, we have a 2 in the denominator. So after that simplification, we will have 1/2, and then the sum as n goes from minus infinity up to infinity of minus 1 to the n times 2n plus 1 times q to the n times n plus 1 over 2. So I just brought this half out. That came from the denominator. Next up, I'm going to split this into two sums. So I'll split it into all of the negative values and all of the non-negative values. So here we have 1/2. And then I'll have this sum as n goes from minus to -1 of minus 1 to the n, and then 2n plus 1, q to the n times n plus 1 over 2. So that's all of the negative values of n, and now we need all of the non-negative values of n. So that'll be the sum as n goes from 0 up to infinity. then we'll have the same kind of argument here. So minus 1 to the n, 2n plus 1, q to the n times n plus 1 over 2. Okay, so now we're almost done with this proof, but maybe we'll finish it off on the next board. So on the last board, we took this q infinity cubed, which was the right-hand side of our goal identity, and we wrote it as 1/2 times the sum of these two sums. And now we'll notice that this guy right here is exactly the sum that we want to get at, but we've got this extra term and our kind of goal over here. So I'll maybe underline this in green and write that this is our goal, is multiplied by 1/2 at the moment. So that's a problem. But maybe we can do some sort of transformation over here that will transform this sum into that sum. And we can, and it is with the following like index change. So we'll replace n with minus n minus 1. So let's see what that does. So when minus n minus 1 equals -1, that means that n is equal to 0. And then as minus n minus 1 is approaching minus infinity, that means n is approaching infinity. So that will have the effect of changing this lower bound to, well, it'll look like positive infinity to 0, but we can just swap them because it's a summation. So it'll go from 0 to infinity. So that's good news. So let's maybe do that first. So we'll have 1/2, and then my sum as n goes from 0 up to infinity of minus 1 to the minus n minus 1. But let's just replace minus n minus 1 with minus 1 to the n times minus 1. Because notice that's minus n to the minus 1 to the n plus 1. And that's the same kind of thing. And then here we'll have 2 times minus n minus 1 plus 1. And then we'll have q to the minus n minus 1 times minus n over 2. And then plus our goal object, which is already good to go, so we won't change that. So now let's see what goes on here and why this is not a problem. So this thing right here can be simplified to minus 2n minus 1. But then we can take this minus sign here, which was extra, and use it to change each of these signs. So we have 2n plus 1. Then next, we can take this minus sign here and cancel out these two minus signs. So we have n times n plus 1. But that means that this guy right here is exactly our goal. So we've got two sums that are exactly the same. We add them together and take half, which just gives us our sum, which is our goal, which is n going from 0 to infinity of minus 1 to the n, 2n plus 1, q to the n times n plus 1 divided by 2. So that finishes the proof of this Jacobi's identity. And now we're going to use this to prove one of Ramanujan's most famous congruences. So we'll finish this video off with the famous Ramanujan congruence, and that is if you have a number of the form 5n plus 4, the number of partitions of this number is congruent to 0 mod 5. In other words, it's a multiple of 5. So just for an example, the number of partitions of the number 4 is 5. Well, that's 0 mod 5. The number of partitions of the number 9 is 30. That's also 0 mod 5. The number of partitions of the number 14 is 135. That's 0 mod 5. Okay, so that's the first couple numbers that are 5n plus 4. Let's talk about one more. Well, the next one would be 19, because that's 15 plus 4. And the number of partitions of 19 is 490, but that's obviously 0 mod 5. Okay, cool. And I want to say that there are a bunch of companion congruences that go along with this. Ramanujan proved quite a number of them, and more have been proven since his time. Okay, so let's maybe jump into this proof. Again, we will use these two identities along the way. But before we get to using those two identities, we want to make a little bit of an observation. So let's look at Q q infinity to the 5th power, but that's going to be equal to this product as m goes from 1 to infinity of 1 minus q to the m, and then that's raised to the 5th power. So this product of these 1 minus q to the m terms come from the definition of this symbol, and this 5th power comes just from this exponent right here. But now we can expand this easily using a binomial expansion formula. So this product as m goes from 1 to infinity of 1 minus 5q to the m plus 10q to the 2m minus 10q to the 3m plus 5q to the 4m minus q to the 5m. So that's just from multiplying this guy out. You could do that the long way if you wanted to, but that also just follows binomial coefficients and maybe Pascal's triangle. But next up, we notice that all of these middle terms are multiples of 5. So this is congruent to 0 mod 5. So that means if we reduce this entire thing mod 5, we get this product as m goes from 1 up to infinity of 1 minus q to the 5m, and this is occurring mod 5. But then we recognize this as one of our special products. This is q to the 5th, q to the 5th infinity. So now dividing some things around, we see that we have the following quotient. So this pockhammer symbol q5th infinity divided by q infinity is congruent to 1 mod 5. And that'll be our good starting tool for proving this congruence. Okay, so let's maybe bring that up and then we'll keep going. On the last board, we built the following congruence, which is a result of the binomial theorem. So if you put these 5th powers inside the pockhammer symbol, in other words, it's kind of inside the infinite product, and divide it by the same thing outside the infinite product, you get 1 mod 5. Okay, so now we can jump into the proof. So we're going to start with q times q to the 4th power infinity. And then we want to manipulate this until we have something that looks like the generating function for the number of partitions of n. So we can do that in the following way. So let's notice that this is congruent to q times q to the 4th times q to the 5th infinity over q all to the 5th infinity. And that's happening congruent mod 5. And that's because we just multiplied by something which we showed was congruent to 1 mod 5. Okay, nice. So now let's make a little bit of a simplification. Notice that these guys will get canceled with all but one of those powers. So that's cool. And that's going to leave us with q and then q to the 5th infinity times 1 over q infinity. And this is occurring mod 5, like I said before. Now, where can we go from here? Well, let's notice that this is q 5th, but then this 1 over q infinity is well known to be the generating function for the number of partitions of n. So this is the sum as m goes from 0 up to infinity of p of m q to the m. This is all occurring mod 5 like we've been doing. Again, p of m is the number of partitions of m. Now, where do we want to go from here? Well, I'm going to take this q and multiply it through, and that's going to give me a p or a q to the m plus 1 here. Now I'm going to take this equality and move it to the top and then start doing a little bit more calculations. We've got this q to the 5th infinity times the sum as m goes from 0 to infinity of p of m, that's the number of partitions of m, times q to the m plus 1 is congruent to q times q to the 4th power. Well, that's infinity mod 5. Now we want to start pulling some things apart so we know exactly what we're looking at and what we want to look for. So notice we want to investigate the number of partitions of numbers that are 5n plus 4. But let's see. the objects that are p 5n plus 4 in this expansion will be attached to q to 5 times something. In other words, the exponent of q will be a multiple of 5. Why is that? Well, that's because if we have a number of the form 5n plus 4 in here, then we'll have 5n plus 5 out here. That's a multiple of 5. But then this object only gives us multiples of 5 in the exponent. So when all is said and done, both of those give us multiples of 5. And so that's why in this big expansion, partition numbers of this form will only be attached to q to the 5 times something. And so that gives us some motivation over here that we need to extract coefficients of things that are q to the 5 times something. And if those coefficients are congruent to 0 mod 5, then we're done. And that's exactly what we'll want to do. And really, to provide a good summary here, what we want is for these coefficients to be congruent to 0 mod 5. And that will actually prove our result. Because notice the coefficients over here that are attached to q to the 5 times something are exactly partitions of numbers that are 5n plus 4. So if we can extract similar coefficients over here and show that those are 0 mod 5, then we've shown that the number of partitions of 5n plus 4 is congruent to 0 mod 5. Okay, so let's erase some of these notes and then we will get to the calculation on this right-hand side. So by our discussion on the last board, we've determined that all we need to do is show that coefficients of terms that are q to the 5 times something on this right-hand side are congruent to 0 mod 5. In other words, they are multiples of 5. So let's get to that. So let's notice over here we have q to the 4th. We know how to deal with q cubed from the thing that we proved at the beginning of this video. So let's maybe expand this so that it includes this guy and then use this identity that we built. So this is going to be q and then q infinity and then q cubed infinity. And this is all occurring mod 5 still. And then luckily we have a way of dealing with each of these. We can expand this one using the pentagonal number theorem, which we proved in the last video. So I'll let you guys check that out again if you need to. And then we can expand this one using Jacobi's identity, which we did at the beginning of the video over there. Okay, so let's expand each of these. We still have this q occurring out front, so I'll just leave that as is for now. So this is going to be the sum as j goes from minus infinity to infinity of minus 1 to the j and then q to the j times 3j plus 1 over 2. So that's from the pentagonal number theorem. Then we'll expand this one using this over here. So that's going to be this sum as k goes from 0 up to infinity of minus 1 to the k, 2k plus 1, and then q to the k times k plus 1 all over 2. And that's all occurring mod 5. Now we'll put these together. I'll bring this q to the 1 inside while we're at it. So that's going to give me this sum as j goes from minus infinity to infinity. And then the sum as k goes from 0 to infinity, minus 1 to the j plus k from multiplying each of those. And then we'll have 2k plus 1. That's coming from this guy right here. And then we'll have q to something that's pretty gnarly, but it's fairly easy to work with. So it'll be 1 plus j times 3j plus 1 over 2 plus k times k plus 1 over 2. And like we pointed out, we want to know about the coefficients of this when the exponents are multiples of 5. So that means we need to investigate what does it take for this to be equal to 5 times something. In other words, congruent to 0 mod 5. So hopefully that forces the coefficient to also be congruent to 0 mod 5. And we'll see that it will. So let's extract that coefficient, and then we'll do a little bit of algebra on it. So I'm going to actually multiply it by 8 because it's a little bit easier to work with if we take 8 times this coefficient. So we'll do 8 times 1 plus j times 3j plus 1 over 2 plus k times k plus 1 over 2 is equal to, so it'll be 2 times j plus 1 quantity squared plus 2k plus 1 quantity squared, and then plus 5 times the quantity 2j squared minus 1. So that's just from fairly simple symbolic arithmetic or like little algebra problem. Okay, but let's notice that we only care about this thing being a multiple of 5, right? Because we want this exponent to be a multiple of 5. That means that if we've got part of it that's already a multiple of 5, we cannot really worry about this. So this is congruent to 0 mod 5 already, so we're good to go on that. Let's just maybe reiterate what we want is for 2 times j plus 1 squared plus 2k plus 1 squared to be congruent to 0 mod 5. This comes back to one of the problems that maybe we did at the beginning of this class. And what we saw is that only certain numbers are perfect squares mod 5. And the only way for this combination of perfect squares to be equal to 0 mod 5 is for each of these individual components to be 0 mod 5. So I'll let you guys check that. Again, that's not too hard to see. It's based off the fact that the only perfect squares mod 5 are 0, 1, and 4. So like I said, we need j plus 1 to be congruent to 0 mod 5. And we need 2k plus 1 to be congruent to 0 mod 5. Oh, but let's look at that. If 2k plus 1 is congruent to 0 mod 5, then we have a very good situation. So let's put a couple exclamation points next to that and then put a box around it. Let's see what we've done. We've shown that if this exponent is a multiple of 5, then this coefficient is also a multiple of 5. But by our previous discussion, that's exactly what we needed to do to finish this proof off. And that's a good place to stop.